You know the song is like, I forget who it is, but it's like a famous old country singer.
Will James.
Is it? Okay. Yeah. Friends. And I think he's the narrator too. Friends, looks like these Duke boys are in a bit of a pickle. And then there's some commercial for Hasbro or something. Okay, so we're kind of done talking about stress and strain. I mean, the bulk of stress and strain we're done with. And remember that these really give the loading and deformation at a single point. And these can give you a really good sense of whether the material is going to break at that point. So these are good representatives of whether the material will break at that point. By the way, we haven't talked about how you use those to determine if the material will break. We haven't talked about it much. And that's because there's a lot of different ways to do that calculation, and you use the different ways depending on the brittleness or ductility of the material. For certain metals, you use one thing. For other metals, you use something else. For ceramics, you use something else. But anyways, with those two bits of information at a point, you can come up with good measures of whether something's going to break or not. But sometimes you don't just want to know what's happening point by point. There's reasons to know what's happening to the overall body. So let's say, but sometimes you need to know the overall deformation of a body. Well, like one example is, so say you build this balcony and you calculate the stresses and strains, and it says nothing's going to break, but then when someone stands on it, okay, it doesn't break, but but it does this, you know? That's still not a good balcony, even if it doesn't break, okay? Not a good balcony.
That'll be a pretty good diving board, though.
Yeah, but okay, but I mean, there's places for diving boards, but there's also places for, balconies that don't do that. So there are cases where just how much, and like, what would you say is the problem with this balcony? I mean, really, the way to think about the problem with this balcony is there's a big displacement between the undeformed position of the end of the balcony and the deformed. And there's also a big difference in the angle of the undeformed and the deformed. Okay, and that's like a macroscopic thing that has all of this thing to do. This, even with this big deformation, it can happen that you get a big deformation like this, and the strains stay small through the whole thing, you know? So you're not worried about the strains being too big. You're not worried about the corresponding stresses being too big, but you get a big macroscopic deformation. And so, okay, beam displacements is what we're working on. And so, like, if this is the undeformed beam, and the deformed beam does this, okay, then the displacement u is the vector from the undeformed material point to the deformed material point. So this is a displacement vector of a single material point. And in a way, you can think of that as like, it doesn't matter, it doesn't depend at all on the strain at that point. It really depends on some kind of integral of the strains over the whole thing. Okay. And so just like we did with stresses, we're going to use the principle of superposition. And the total displacement at a point is going to be the displacement due to internal tension, plus a new one, the displacement due to thermal changes, plus the displacement due to the bending moment. We skipped the shear force on this one, and only the bending moment matters. That maybe isn't such a surprise. I mean, I said that this displacement depends on some kind of integral over the whole thing, and you know that there's an integral relationship between shear force and bending moment. So you can think of the shear force as sort of baked into this bending moment displacement, and then plus the displacement due to the torque. Also, maybe the more interesting use of this, these displacement calculations can be used to solve statically indeterminate structures. Okay, so for example, let's think about a structure, you know, the kind of structure that we would have done in statics. Let's say there's some force applied. All right, is that Well, is that a structure or a linkage? Since you're so great at this. um, right. So that's not going anywhere, right? Nothing's going to accelerate. Actually, you know what? Let me change the direction of this force and then you'll believe me. Okay, that's not going anywhere. The other one actually would have tipped up. But it's a very reasonable thing. I mean, if your boss says, okay, build something that keeps this structure and I don't care what you do, make sure it doesn't break, it would be a very reasonable modification to hold on. Put a reinforcement in here. Like that, right? I mean, so anytime you take something that is already going to be rigid and add additional, strengthen, add additional loads to it, additional constraints to it, you get something that's statically indeterminate. So this you could use statics for. This, if you went through all the statics that exist, you would come up with more variables than equations. So that's the definition of statically indeterminate. More variables than equations. And it turns out that because those joint constraints require that those, all three of these members need to meet at exactly that point, these two members need to meet at exactly this point. And so if you can include information about the macroscopic deformation of this thing, say this piece, according to the loads applied to it, then you can figure out what loads need to be applied to the different things to make them still, meet at that joint. Okay, so that's the idea of using this for statically indeterminate structures. Okay, so here's a roadmap for what we're going to do in this topic. First, we're going to talk about displacements due to tension and compression. And I'm going to lump in here, since it kind of acts the same way, thermal expansion too. And we're first going to talk about how to calculate displacement. And that you can think of as elongation or contraction. And then second, we're going to apply this to statically indeterminate structures. And so we're going to do that whole thing with tension, compression, and thermal expansion before we go on to the next thing, which is basically the same version of this, but due to bending moments. So first we're going to talk about beam deflection. Beam deflection is like the vertical distance from the original location of the material point to the new location of the material point. And then we'll apply that to statically indeterminate structures. And then finally, torque. And we'll talk about this in terms of the angle of twist. And then we'll apply that to statically indeterminate structures. Any questions about our plan for this topic? Okay, so first we're going to get into tension, compression, and thermal expansion. At a single point, the XX stress in a beam is equal to the internal tension divided by the cross-sectional area. And the relationship that we get between stress and strain says that the normal stress in the long axis, the normal strain in the long axis of the beam is equal to 1 over E times the XX stress. So we can write this as T over EA. And then if you think of the definition of the strain in the limit, this strain is equal to like this is the formula we've used, right? But in the limit, as you go to this infinitesimal distance, L0, to define the strain at a single point, you can think of this as the derivative of the displacement divided by, du dx. The derivative of the displacement with respect to x. And so we can say du dx is equal to t over EA. Separate and integrate, du is equal to t over EA dx. And so the displacement is the integral over the length of t over EA dx. So that's the integral definition. And so when do you have to use this? There are times we are going to have to use this integral definition. You have to use it if t, e, or a vary continuously. If the beam can be separated into pieces with constant values of T and E and A, you can use like a finite formula that comes from this that says U is equal to the sum over all these n pieces of the tension on a single piece times the length of a single piece divided by the stiffness of a single piece times the cross-sectional area of the single piece. Okay, so let me do an example. I guess I'm going to do two examples, one of each of these two types. The first one is, let's say we have this pole and let's say we have at the midpoint a 10,000 Newton force, and at the top a 3,000 Newton force. And let's say this is steel, so for the whole thing, the stiffness is 200 times 10 to the 9th pascals. And the cross-sectional area is 0.01 meters squared. What's the displacement? at the top of the pole. Since we're used to picturing these sideways, I'm just going to redraw this. So let's say I tipped it over, or I guess a better way to think of it is I tipped our heads counterclockwise. Okay, so the ground is over on the left and the 3,000 Newton force is on the right. So we have this force here, R, and then we have a 10,000 Newton force here, and a 3,000 Newton force here. This is a free body diagram. I'm going to use Newton's second law in the x direction. So we have R plus 10,000 minus 3,000 is equal to 0. So R is equal to negative 7,000. And now we can do our cuts. Okay, so how many cuts do we need? 2. The first cut is valid. Oh, I didn't give a length. Let's say this is 2 meters long. Okay, so the first cut is going to be valid for x's between 0 and 1. And the cut looks like this. We have 7,000 this way. And since we haven't gotten to the 10,000 yet, our only other force is that internal tension, T. And so Newton's second law, I'm just using the x component, says negative 7,000 plus T is equal to 0. So the internal tension is positive 7,000. And this looks a little different than how we've done internal loads before, but I mean, you could do the full method and show all those internal loads. The only one that's going to be non-zero in this setup is the internal tension. So that's why I just sort of simplified it, but I haven't changed anything really. I'm just calculating the internal loads. Okay. And then for cut 2, this is valid for x's between 1 and 2. We have the 7,000 Newton force that way, the 10,000 Newton force that way, and the internal tension. So negative 7,000 plus 10,000 plus T is equal to 0. And so T is equal to negative 3,000. Okay, so now we have the internal loads. And now we have to ask ourselves, do we want to do this piecewise formula? Do we have constant values of T, E, and A over finite pieces? Or do we need to do this as an integral? We have 2 different sections where on each piece of this beam, T, E, and A are constant. So I'm going to use the sum formula. Yeah.
So would we use the integral when there's maybe like a distributed load or something?
A distributed load, yeah, although, yeah, that's a good thought. We could use it for a distributed load. More often, we would use it for a continuously varying cross-section, something that's a little thicker on one end and thinner on the other end.
Gotcha.
So that's the example I'm going to give. But yeah, distributed load, well, we haven't done any problems with X components of distributed loads, have we? Did we do that in statics?
Yeah.
Okay. So you can do that. Well, maybe that's another thing. If we have extra time at the end, we could do a little more work with that. Okay. So T, E, and A are piecewise constant. So we're going to use the sum formula. And that says the displacement at the end of the beam is equal to, for piece 1, we have a T of 7,000. A length of that first piece is 1 meter long. Divided by Young's modulus and the cross-sectional area. Okay, and then we're going to add that to the displacement for the second piece, which has an internal tension of negative 3,000, a length of 1 meter, Young's modulus of 200 times 10 to the 9, cross-sectional area of 0.01, and you get a value of positive 8.5 times 10 to the minus 6 meters. So 8.5 microns. The positive value means elongation. If we get a negative value, that means contraction.
Kyle,
Yeah.
how exactly does meters pop out if we have like a Newton which has a kilogram in it?
Let's see. We have, so yeah, the 7,000 is newtons, but that Young's modulus is 1 over, I guess it's in pascals. So the newtons cancel there. You have a meter squared on top, meter on, I don't know, it works out.
Okay, it's got the force over area for the Young's modulus.
Yeah. Any other questions about that one? Okay, so now let's say we have a piece with a continuously varying cross section, and on this side we have 20,000 newtons, and on this side we have 20,000 newtons. And let's say that the length is 1/2 meter. And let's say that over the whole thing, it's a square cross section. That goes from a length of 1 centimeter on each side to a length of 6 centimeters on each side. And we want to calculate the elongation. Well, can you look at this and tell what the internal tension is? It's just going to be an internal tension of positive 20,000 over the whole thing. There's only one cut we need to do. But of course, if you don't see that, you could go through the cuts and whatever. One thing that we have to do is, okay, so this is varying continuously. With x, right? So we're going to need to use the integral definition. And so that means that we need tension, internal tension is a function of x. Young's modulus is a function of x. And the cross-sectional area is a function of x. I didn't give the Young's modulus. I guess I assumed steel again. Well, the internal tension is the same everywhere. So that's just a constant function of 20,000. Young's modulus is just a constant function of 200 times 10 to the 9th. But we do have to figure out the area as a function of x. Okay? So one way we can do that is just figure out the equation of a line as we go from, so as x goes from 0 to 0.5, let's call that the side length. Okay, so we're going to start at 1 centimeter, and we're going to go to 6 centimeters. And so there's our function of the side length of that square. So what is it as a function? Y is equal to mx plus b. B is equal to 0.01. For the slope, go rise over run. So we have the rise is 0.06 minus 0.01. The run is 0.5 minus 0. And so you get 0.1. And so the function of that line is 0.1x plus 0.01. Okay, and that's the side length. This is a square, so the area is L squared. And so we're going to have to FOIL this out. Have any of you guys have had math professors that have been really like unnaturally belligerent when people said to FOIL stuff out? Have they? Yeah, because for some reason math teachers really don't like that. Okay, well, distribute these things through for those math teachers. I'm going to call it foiling it out still. I think they feel like you're remembering a rule instead of just thinking about what it is, you know. But I think you can think about what it is and still call it foiling. Did you learn foiling or no? Yeah, foil. First, outside, inside, last.
I just did first, inside, outside, last. Until like last year.
That's fiol, that's not a word. You never learned foil? Did you learn the box? With the four?
Oh, yeah.
Okay, yes, the people, you either learn foil or you learn to write out that box. My son learned the box, but...
Yeah, mine was always like, I was like doing it in my head just to see if I could, and then
Oh, yeah.
write the box after.
Oh, yeah.
You get points marked off, you don't show like
Right.
the process you have to do.
Right. Yes.
Are they still teaching lattice multiplication?
I don't know what that is.
Is that just like a multiplication table?
No, it's like you have to set up the numbers on the outside, you have a grid, and then it like.
No, I've never heard of that. I don't know. Uh-huh, yeah. Okay, so we got 0.01x squared plus 0.001x plus 0.001x plus 1 times 10 to the minus fourth. And so that is 0.01x squared plus 0.002x plus 1 times 10 to the minus fourth. So that is the area as a function of x. And so now we can write out the displacement. So the displacement, this is just a displacement along the x direction. I'm going to take that off, but this is equal to the integral. For x values from 0 to 0.5 of our internal tension as a function of x, that's just 20,000. Dx, I'm just looking at my formula for a sec, yeah. Okay, divided by the Young's modulus times the area. So this is 0.01x squared plus 0.002x plus 1 times 10 to the minus fourth.
Would it make it easier if you factored out 0.01?
Yes, it would. And so we can pull all the constants out. So I'll do that first. So 20,000 divided by 200 times 10 to the 9 divided by 0.01. And so if you pull all this out, you have 1 times 10 to the minus 5 times the integral from 0 to 0.5 of dx over, and now I think really I should have just kept that factored instead of multiplying it out. That comes out to be x, what does that come out to be? X plus 0.01 times x plus 0.01. No, I'm looking at the wrong stuff. So if you pull out 0.01, I think it's this, right? And now, now you can say, I'm going to use U substitution, but I'm going to call it something else because, well, let's just call this the displacement delta. So U, for U substitution, is equal to x plus 0.1. So du dx is equal to 1. And so dx is equal to du. And so delta is equal to 1 times 10 to the minus 5th times the integral. I'm going to just change the boundaries to u right now. So if you plug 0 in for x, you get 0.1 here. If you plug 0.5 in for x, you get 0.6 here. And now we have du times u to the minus 2. And that's 1 times 10 to the minus 5 times negative u to the minus 1, evaluated from 0.1 to 0.6. And so our elongation is 1 times 10 to the minus 5 negative divided by so point, what's going on here? Why do I have that negative sign there? One over point.
I think you have a negative smaller number dividing by 0.6, and then we're subtracting a larger negative number.
Okay, right. Yeah, okay. So okay, so I got this, and I'm going to multiply by 1 over 0.6 minus 1 over 0.1. And you get 8.3 repeating times 10 to the minus 5th meters. Okay. Any questions about that? So if any of those variables are varying continuously, you have to use the integral form. If they're not, then you can use that sum form. Yep.
Are we generally gonna be dealing with like very small, deformations like this, in like the micrometers and stuff, such?
Yeah, I mean, if you had a bar that was 50 miles long, you could have, small strains and small stresses the whole way and still have a big deformation at the end. But yeah, mostly, I mean, if we're talking about steel, like you can have a pretty long piece of steel and still make it pretty hard to notice a deformation, We'll get bigger ones with deflection. But it all depends on what parameters you use. If we made it a millimeter thick, and really long, you could get big deformations.